not have a chance to attend today, but they ask if possible. So I'm recording this and I will post it on our YouTube channel. Again, welcome to our March installation of SpaceGeekSpeak. SpaceGeekSpeak is a regular Saturday engagement platform, and it's sponsored by Houston AAA section, but everyone is welcome. You don't have to belong to Houston section. We will have you, if you have any questions or if you just want to have a discussion, you are always welcome to join us every Saturday, 8:30 till I publish it as till 9:30, but we never cut it off at 1 hour unless absolutely have to. So there's this platform is open for us to engage, collaborate, and to support each other. With that said, welcome to Paul's team. I am pretty sure that Paul will introduce everyone, and we are waiting for your presentation. Go ahead.
Yeah. Thank you very much, Svetlana, for the introduction for everyone. So we are a team of Cranfield students, university in the UK. We are doing a MSc in astronautics and space engineering. And so this is our presentation for our group design projects. And I think I will give the hand to Flavine so that we start the presentation. And yeah, for your information, it's about 1 hour and a half approximately, a bit less as 1 hour and a half. So Flavine, if you can now start to share your screen and we can go on, I think.
There it is. I hope everyone can see it. So yeah. Our presentation is, as Paul said, for our GDP, and it is titled the Lunar Meteorite Hunter. So I just want to start by saying, talking about the team first of all. So we are a group of 11 people with our supervisor called Dr. Marta Ceccaroni. So we decided to divide our team into 5 work packages that are namely here system, mission, mechanical, electrical, and payload work packages. And okay, so I hope you can hear me properly. Okay. So here's the list obviously of all of our team members who are here today, and they will later speak about more of their work package. So the first thing I want to talk about is our design strategy. How did we go about making our decision, and how did we start doing our design? So we decided to follow what's called the double diamond strategy, which starts by we start with an exploring phase where we suggest different ideas and we research different possibilities to answer the question that we're asking ourselves at the beginning. After we have a wide array of ideas, we can start defining a bit more specifically what we want to make so that we can start on with the step 3, which is the development of the concept, where we have our final product in mind and we're trying to do all necessary calculation and testing to prepare for it before the final stage, which is called the delivery of the design. So this is our Gantt chart, and here I want to show that our project essentially started mid-October, as you can see at the top. And
there is a sound in the background. If someone could mute, I don't know who is it, but yeah, could be cool for Flavine. Thank you. Go ahead.
Thank you. So yeah, as I was saying, our project started essentially mid-October, and we plan to end it normally next week. So first of all, we need to comprehend where we're going. We're trying to do something that is going on the moon. So there's a lot of problems with the lunar environment. So we just want to go quickly over some of the obvious ones. So obviously, first of all, there's the extreme temperature fluctuation on the moon. So some measurements taken by Apollo 15 mission gave a maximum temperature of about 100 degrees and a minimum temperature of about 180 degrees. But as you can see, the temperature can vastly depend on the position of the site of the mission, but also on the distance between the sun and the moon. So that is something to take into account later on. We also have to consider the sidereal rotation of the moon. So essentially a complete cycle of day and night on the moon is about 27 Earth days. So that means that for us, the day is going to last about 14 days. Another thing to consider is the low gravity on the moon, which is much lower than the Earth. So that can be actually quite beneficial, meaning that our forces obviously are going to be a bit lower. Another thing to think about as well is the lack of atmosphere on the moon, which is technically a misnomer. There is an atmosphere on the moon, but it is very, very small. During the lunar day, it's about 200,000 molecules per centimeter cube. And whilst it may seem like a lot, it's actually 14 orders of magnitude less than the Earth atmosphere. So that's why we usually say there's no atmosphere on the moon. Another thing to consider is the ionizing radiation that you can have on the moon. So there are three main types of radiation: the solar wind particles, solar flares particles, and the galactic cosmic rays. So the solar wind are typically large fluxes with low energy. The solar flares are very intense but quite rare. And finally, the galactic cosmic rays are low fluxes but very high energy. Now, there are obviously other types of radiation that hit the moon, but usually because they're such low fluxes and such low intensity, they get very difficult to detect. So we don't usually take those into account. Now, obviously, those three radiations don't actually typically penetrate an object for more than a few centimeters at best, depending on some of them. However, the galactic cosmic rays can be a bit more challenging because they have some heavy nuclei that can damage sensitive electronic components. But usually, thankfully, a few centimeters of shielding is enough to cover and to protect what we need to protect. If anything, actually, those radiation can be quite interesting, as the amount of products from the solar flares and the galactic cosmic rays can be used to determine how long a sample has been under the surface of the moon, depending on if they've been under micrometers, meters, or centimeters under the surface. Another thing to consider in the lunar environment is the occasional bombardment of micrometeorite. But this one isn't too much of a problem, thankfully, because some lunar orbiters, the lunar orbiters, 1 through 5, measured perforation due to meteorites that they received during their mission, and recorded an average of 0.16 perforation per meter squared in a day, which is about half the amount that an orbiter would receive if it were near Earth orbit. So that one isn't too much of an issue, and we usually know how to deal with them. And finally, our biggest enemy is the lunar dust. So those grains are usually between 15 and 100 micrometers. And many of those grains are very sharp and glassy. And most people make analogy about them as if they were very fine grained slag or like terrestrial volcanic ash. The problem with those is that they permit accumulation of electrostatic charges, which means that dust can accumulate and adhere to objects, as has been demonstrated by further examination of the Surveyor 3 robot lander, which had been sent in 1967 on the moon and then visited 2 years later by the astronauts of Apollo 12. So why are we doing our mission, really? It all started thanks to ESA's call for idea. So ESA often calls for ideas to answer a simple question. And in this case, it was, what would you do if you had the opportunity to put a payload on the moon? Using ESA's European Large Logistic Lander, also called ER3. So this lander can deliver about 1.5 tons of payload on the moon. ESA called for ideas to put payloads on that lander and hopefully send it between late 2020 and late 2030. So here comes our idea. Our proposal was to design and send a rover to retrieve meteorite samples and bring them back to the EL3 for more complete analysis. The idea would be that the lander would also be provided with a lab on board that could do much further chemical analysis with a very power-hungry payload that a rover wouldn't need to carry. So in order to estimate how much meteorites actually fall on the moon, we started by using the NELIOTA program by ESA, which can help to determine some meteorite landings on the moon, and also does the same thing for the Earth. and it's great to be able to, it's great to use in order to locate the best impact sites. So knowing the conditions on the moon and knowing what the start of the mission will be and trying to answer ESA's idea, we can start with a few initial requirements. So obviously the rover has to be able, like our hunter actually has to be able to survive the lunar environment. So survive the night, survive the radiation, survive the extreme heat fluctuation and the lunar regolith, again, our biggest enemy. But from the lander, we also know that we have to be under 500 kilograms. And the reason why 500, not 1500, is because we don't want to take too much space, as in theory, the lander should be used to be shared for other payloads that also answer ESA's call for idea. So we gave ourselves a limit of 500 kilograms. We also want obviously to fit inside the lander, so we do not allow ourselves to go further than, we have to fit within the 4.5 diameter shell of the lander. And finally, an extra issue, an extra constraint here is that ESA does not typically use nuclear decay.
So
we decided to avoid.
We are losing Flavin. The connection from the moon. Yeah, we are losing you. The connection from the moon is not always working. So that's the main challenge.
Sorry.
Space. Yeah, you can go ahead. Yeah.
Oh, sorry. Can you hear me again? Sorry.
Yes.
Okay, good. Where did I cut?
We lost you at the nuclear decay.
Yeah, essentially, because ESA does not use any nuclear decay to power any of their system, we decided to avoid using RTGs or any other form of power system that relies on nuclear decay. And based on that, we decided that we want our mission to last about 180 days. So there it is.
Right. My section kind of unfortunately massively repeats a lot of Flavin's section. We haven't completely gone over everything, so I might make mine a little bit shorter so I don't repeat things as much. I was me and Flavin were the two systems people on the project, and I was looking initially when we looked into it. We were doing the initial mission analysis and project drivers for the project. Now, initially, when we began the project, we were using only LISA data points to find samples, which there are only 167 on the Earth-facing side of the moon. This meant that they were hundreds, if not thousands, of kilometers apart, and it created a little bit of an issue because the furthest any rover has traveled is Opportunity, and that took it 14 years to travel 45 kilometers. So we also realized from this that if we wanted to complete it in this function, we were going to have to survive during the nights. And it's not a problem surviving in extreme heats or extreme colds, but doing prolonged for both is incredibly difficult. And normally it's a big issue. And obviously the other main challenge was the radiation. Could you flick over, Flavin? So most of the equipment on board needs to stick between 0 and minus 40 degrees centigrade. I'm sorry, American people, I didn't put the Fahrenheit version, but it's not a problem keeping a system warm by using such something like an RTG, which we couldn't have used anyway. But the main issue with that is if you do want to use that as your main power source, you can't turn it off, and then when it gets very hot during the day, it's incredibly difficult to then maintain its temperature. And as brilliant as solar panels are on the moon, the only problem is to have a battery that would be sufficient enough to keep it warm during the night is very challenging, as it's 13.5 days. Also, the other main challenge with something like an RTG, if it was even available to us, is they cost over $1 billion, which for a project like ours is not feasible. Flavin? Yes, so this is kind of going over what I previously said. And the LETER program's only got 167 collisions that it's recorded. And these are spread out all over the moon. And we realized soon in the project that one of the things that we weren't considering is actually that there is about 600 million craters on the moon with different variety sizes, and actually there might be over 1 billion actual meteorite landings that have happened over the last 5 billion years, and that these actually could be used as well to find out valuable information. So we realized in the project that it might be better to not just use the LETER data, but actually to only use one of the LETER data points and then travel to these craters that were in local vicinity, and therefore we could collect a lot more meteorite samples, traveling only a fraction of the distance and needing very little time. Flavin? When on the moon, or to be honest, in space in general, radiation is always a very large issue, but the moon is obviously particularly susceptible. We were, Flavin already mentioned the various types of radiation that it's exposed to, but all you can do is try and limit the exposure to your main systems that such as your electronics and your instruments, which will be heavily affected by using protective shielding and using radiation hardened chips. Flavin? It was very difficult actually to do my budgets for this mission, mostly because there haven't been many missions to the moon for rovers, and Mars is a completely different environment, and most of the more recent Mars rover missions have used RTGs as their power source, and they are designed for many years and have a very different type of mission. So instead, what I decided to do was I viewed all of the different rover systems and approximated what the mass percentage would be for the payload, and I worked out approximately what a level of payload mass would be and worked backwards for that from there. As much as we have an opportunity of using 500 kilos, I don't think that amount is necessary for the mission, and obviously keeping the mass as low as possible is beneficial. So we're looking to keep the mass of the rover down to about 300 kilograms. It might be closer to 350, but that's what we said. And I've put a budget of $200 million for the mission, but again, that's a very early desire. I think that's it for now, because a lot of all the work that I've done is in, oh no, I've got the project timeline. So this was for the first 40 hours of the day. During our mission, the first 24 hours, we're not leaving the habitat, the lunar lander, because it's very cold and our thermal systems just couldn't cope with the cold temperatures, and also without a high level of sun, the power generated will not be sufficient enough. We're hoping to travel at about 180 meters an hour, which is quite reasonable, but we've also decided that we'll need an avoidance factor for traveling around craters and obstacles that we can't circumvent, and we made that 0.5. So this section here is for traveling between for a crater that's about 90 meters away, and then these are the different modes which Valentine will later on explain, and this for the collection and storage of a single of 5 samples from one crater, and that's very close to the lunar lander. Thank you for listening.
Good morning to all. I'm Akshay. I'll be presenting the science package of the payload. So let me just give you a brief background about what meteorites are and stuff like that. So meteorites are just extraterrestrial rocks that fall into our atmosphere, and meteors are the light that it produces, and meteorites are what actually makes it to the ground. And initially there have been like many types of classification of meteorites, and the most common one that you might have heard is that the classification in terms of composure, which is the stony meteorites and the iron meteorites. But the best way to classify them is based on the presence of the chondrules. So there are like two classes of meteorites, chondrites and achondrites, and the chondrites are the largest class of meteorites based on the sheer number of impacts. And these meteorites show like little to no differentiation. On the other hand, the achondrites, which include the which include the meteorites from the asteroids, moons, and planets like Mars, they are very rare meteorites, and they have like less number of folds. Fleming, can you go to the next slide? Fleming, yeah. So the important question here would be like, how do we tell them apart from the terrestrial rocks? So we can differentiate them by looking them, I mean, visually, like, but that would be hard. The other way of telling them apart would be like based on what minerals they have. So the main minerals that most meteorites have are olivine, pyroxene, and some iron nickel minerals. So we can use this information to identify these meteorites. Next slide. So yeah, so the history of the solar system is locked within these planets, asteroids, and other objects that orbit around the sun. So most of the geological and geochemical information regarding the formation of the solar system and such things is within these meteorites. So if you look at the graph that's been shown here, it is the distribution of the elements in a particular carbonaceous chondrite, and it is compared to the distribution of the sun. So as you can see, it is almost coincides it. So you can see that it makes a lot of sense why we show so much interest on meteorites. And the image in the bottom shows the difference between the terrestrial planet and the basaltic body of an achondrite, which also shows a lot of similarities. So that is why we look for meteorites. It can unlock the secrets of the planetary formation. Next slide. So there was also a case of terrestrial meteorites, which basically means the meteorites that originated from Earth. So it is of particular interest because I mean, why not? Because these meteorites were formed like 4 billion years ago, and it can tell us a lot about Earth's geological transformation from 4 billion years to now. And most of these meteorites that are actually found on Earth have been like weathered severely, and it is estimated that like 500 kilograms of these meteorites per kilometer square are deposited all over the moon. But the only problem with that is that they are buried deep underneath the lunar regolith, like tens of meters inside. So we are planning to use one of our instruments to gain some information on it, which will be discussed later. Can go to the next slide. Yeah, so for identification of meteorites, we basically use like 2 different scientific methods. One of them is the spectrometric analysis. Will be done in order to identify what minerals they have. This operation will be done both on the rover and the lunar laboratory, which the ELL3 has. So the next one is the petrographic analysis, which will be done using a petrographic microscope in order to analyze the geological data of the sample into categories, so that we categorize it, and we will be able to make a decision whether or not to bring it back to Earth. Next slide. So the spectroscopic analysis, we use like 3 or 4 spectrometer, which has Raman spectroscopy, Mossbar spectroscopy, and these are all done in order to estimate the amount of iron present. The Mossbar spectrometer in spectrometry generally is used for iron-bearing minerals, and as you can see, this graph gives us the difference between the meteorites and the lunar achondrites. So the blue ones are the lunar achondrites. Using these, we can identify which one of those are meteorites and which one of those are just lunar regolith. This method can be real. It will really come in handy when we are in the rover. Next slide. So the petrographic analysis is basically a method in which we just take a thin section of the sample and we clamp it between the polarized sections, and we use a petrographic camera to analyze it. And this can give us the granular structure, which can be used which gives the morphological characteristics of its microstructure and a lot of information the geologists can use. Next slide. So there are like two projects that I've been using for estimation of the landing site and such. So one of them is a NASA project which is called Lunar Impact Monitoring one. So Neliota and the Lunar Impact Monitor use a similar kind of telescope, but the only difference is that Neliota uses a dual coronary camera, so it gets both the R and I spectrum of the photometric analysis. So using that, we have obtained like 113 flashes in 169 hours, and we've been able to plot the distribution of all these meteorites all over the moon surface. And these data have been used to obtain the temperature, mass, and impact corridor of these meteorites. Next slide. So yeah, it is just what I said in the previous slide. It is we've able to obtain the impact temperature using RI photometry, and the mass of meteorites using some of manipulations, and the other important parameters we took into consideration is the crater diameter and depth. It'll be very useful in order to know whether a rover can actually operate in that slope, and what kind of mass we can expect from a crater of that size. And it is basically used to estimate what the kinetic energy of a projectile would have been, in order to find out if the meteorite would have survived the lunar impact. Next slide. So the crater information is another important thing, because like we are solely not relying on the Neliota project, because the distribution is so sparse that reaching from one meteorite, one crater to another, just based on the Neliota project would have been really impossible. So what we decided is that the lander would have a camera which would capture the surroundings of the meteorite, I mean the impact, and we can look at other craters and compare their diameter and come up with an estimate of their mass, and check whether if it would be suitable for us to collect samples from them too. So for that, I've used like Maxwell's Z model crater excavation model to estimate what mass it would have been and what depth it would have been, using the diameter alone. Next slide. So the other important thing would be the survivability of the meteorite. So according to the information I got from Neliota and the Lunar Impact Monitor, it's been noted that most of the meteorites that strike the surface of the moon are within the range of like 20 kilometers per second. So it is my belief that there would have been a lot of meteorite impact much below this velocity, because the telescope that we use for detecting the meteorite impact cannot estimate an impact which has a magnitude of more than 12, which means the dimmer impacts will not be counted. So some of the low velocity impacts would have been not accounted in these lunar impact monitors. And that is why I think it would be apt for us to look for meteorites in the moon, because it can be very much survivable. Next slide. So this is just the distribution of how different meteorite showers go in the moon. So as you can see, it is a lot concentrated on the equatorial region. It is like -20 to 20 of the latitude. So we would be concentrating on this part, and the different colors mean different showers, which I think I missed to put it in the slide. Can you go to the next slide? As you can see in the graph on the right side, I've selected like 4 different showers based on their velocity, their zenithal hourly rates, and their mean mass. So the landing location was selected based on several criteria, which is shown on the left. Like it was mainly focused on the equatorial region because that is how it was proposed, and that would be apt for the power consumption too. And, and the impact the graph shows the impact corridors of different showers. As you can see, the solar longitude is nothing but the position of Earth or Moon according to the Sun. So a solar longitude at 0 starts on March of 21st, which is the vernal equinox, and ends at the sometime around the same time. As you can see, the Gemini shower, it mostly impacts on mid-October, date like that. So I've taken a lot of things into consideration and come up with one actual site, which has a good possibility of survival, and it will be presented by Najwa in the next slide.
Good morning, everyone. I'm Najwa, and I was responsible for the landing site selection for our mission. So as we can see here, the slide shows the general process of landing site selection. So firstly, the scientific objectives of the mission and the engineering constraints will be the main factors from our selection. So from the scientific objectives, the specific requirements for the landing site, such as the geographic location, the geological states, and the space environment were defined. Also, to ensure that the mission would be a success and for a safe implementation of it, the engineering constraints of the geographic location, the space environment were refined in terms of engineering reliability. Also, we've got data from all the previous missions and all the photos from the previous landing sites and data from the Lunar Reconnaissance Orbiter. And the selected potential areas meeting all these requirements will be scientifically evaluated and scored, and the site with the top score will be selected as the proposed landing site. Next slide, please. Thank you. So the first step was to came up with potential landing sites. So we've got like 10 potential landing sites that were selected based on their scientific interest, meaning that they were close to areas that have a high concentration of meteorites impact from the Meteorites program data and have a high density of olivine, which is the main component of the meteorites we are going after. Also, these landing sites were based on flat surfaces with an average slope of 8 degrees and are being sunlit for at least 14 days and are visible to Earth all the time for radio communication, and are not having any large hills or high cliffs that can cast shadows for long periods and that can endanger our landing or just cast shadows and endanger our power generation. Next slide, please. So the first step was to decide which meteorites we were going to collect. So the one we were going after are the one from the Meteorites program. And the Meteorites program had just 60 meteorites impacts that were qualified as really true or verified impacts out of 167 impacts, total impacts for the three last years. So while placing all these impacts on the LRO map, we just find out that just 5 zones that have like a cluster of 2 to 3 meteorites that were relatively close to each other compared to the other ones. Next slide, please. So in order to know how many meteorites we will be going to collect and how we are going to do that, I try to calculate the distance between the meteorites within the same zone to see if it's really feasible to just collect all of them or go just after one. And I found out that the really closest are 21.7 meter. Sorry for the typo, it says kilometer. So they are, oh no, sorry, it's 21.7 kilometer apart. So that distance was really far for our rover, and our rover wouldn't be able to do that, to travel all this distance. In fact, all the rovers that went to the moon or Mars wouldn't be able to do that. And so we were going to go just after one meteorite from this program. Next slide, please. So as I said in the previous slide, we were going to have just one meteorite from the Meteorite program. So we had to make sure that this meteorite really exists and survive the impact, because sometimes the meteorite can vaporize upon the impact. So the science team performed a more in-depth study for the meteorite showers, and as Akshay explained in his section, and came up with the coordinate for the meteorite that has the highest probability of really existing and surviving the impact. So after giving me the coordinates of this meteorite, I came up with the landing site based on solely the scientific interests. But fortunately, the landing site fulfilled all the requirements, from a slope that is less than 8 degrees, a continuous visibility of the Earth for radio communication, and being on the near side of the moon. Next slide, please. So we decided to have a domain of operation that is that does not exceed 4.5 kilometer radius. And we decided that after collecting the meteorite from the Meteorite program, the rover will exit also the lander again and go to inspect all the craters that are nearby, to search for meteorites that were older than the Meteorite program or were just not detected by it. So we chose the 4.5 kilometer for our domain, so the rover will have a kind of safe environment to explore, because all the craters in here does not exceed 2 meters in depth, and the majority of them are 7 to 12 meter in diameter, which makes them really compatible with the mapping strategy we will be using, and also to ensure that the rover will not lose communication with the lander. Yeah, that's it.
Thank you, Najwa. Hello, everyone. I'm Valentin from the Mission Work Package, and I will present you the scenario the rover will follow. So the landing phase starts. At this point, the rover is inside the lander. He is in the hibernation mode, where he uses only the communication equipment in order to interact with ground control via the lander. While landing on the chosen landing site, the camera on the lander will be used to compute multiple trajectories, to get to the craters that we need to study, and gives these trajectories to the rover. After the landing, the rover will be able to exit the hibernation mode after a total checkup of the rover and approval of the ground control. If there is any anomaly, the rover will go into safe mode until the ground control fixes the issue. Next slide, please. Thank you. Once the rover is certified as problem-free, the rover will go on the lander and will go off the lander, and can start its travel mode to get to the position given by the lander while landing. During this mode, the rover will use its mast cam, motor, and wheel equipment to get to the desired location. So, as Najwa stated, our first location is the Heliotas crater. Next slide, please. Thank you. Once arrived, the ground control will have to check if the rover is at the wanted location, which means that ground control will need to determine if the rover is indeed at less than 10 meters of the crater that we want to study. Ground control will therefore allow to exit the travel mode to enter the identification mode. The goal of the identification mode is to determine, with the help of the cameras on the rover, if the crater is accessible so the rover can climb it without fearing to fall upside down. If the crater is too dangerous for the rover to access, the rover will go to another crater chosen beforehand according to the size, depth, and travel distance to this crater. Otherwise, the rover will enter the wayback mode if no crater are reachable in an appropriate amount of time for the mission. However, if the crater is accessible, the rover shall climb the crater and stop on top of it. Once the top reached, the mapping mode may proceed. Next slide, please. Thank you. The goal of this mapping mode can be divided in two objectives. The first one is achieved by the mast cam. The goal of the mast cam is to take a 3D colored picture of the crater. This way, the ground control will have a better understanding of the rover environments. And also, this picture of the crater will be used to determine the spiral pattern needed for the next mode. The second objective of the mapping mode is achieved by the supercam. The supercam will do a mapping of the chemical composition and concentration of the crater surface. Once these two operations finished, the mapping mode shall end and the crater mode will start. Next slide, please. Thank you. So during the crater mode, the rover will go down the center of the crater and will use the rimfax. The goal of this mode is to obtain a 3D density map of the volume directly under the crater. This map shall cover the whole crater. Therefore, either ground control or a slope inclination condition of 20 degrees will stop the rimfax operation. The area covered by the rimfax being approximately the width of the rover, the vehicle shall enter a spiraling outward pattern starting from the center of the crater. This spiraling outward pattern, will be determined by the 3D pictures that the mast cam previously took in the previous mode, in order to cover the whole crater's area. Also, for the mission objective, up to 5 samples of 72 cubic centimeters can fit in the sample box, inside the rover. This will be stressed out by the mechanical rover package. Once the rimfax has finished its mapping, multiple scenarios will occur. The first one is if no changes in density has been detected under the crater. Therefore, it means that the only relevant meteorite material that we can collect is located on the surface, as dust. So the previously executed supercam mapping of the surface will now play its role. The rover will go to the 5 locations of the crater with the most meteorite material concentration and proceed to the sampling. If no such location has been detected by the supercam, it means that according to our equipment, there is no trace of meteorite in this crater, and therefore we should go investigate on another one. The second scenario is if there is indeed density changes under the crater surface. These changes may be, so if there is density changes, they may be meteorite pieces. Therefore, depending on the number of these density changes, the rover will go up to the 5 location with the highest density and proceed to the sampling. Next slide, please. Thank you. So now, once the rover has reached one of the locations previously mentioned, so a high density zone or high concentration zone, the rover will proceed to the sample collecting mode. During this mode, the rover will use its drill to take samples. The samples will then be stored in the sample box previously mentioned that will be located right next to the drill. Again, all this operation will be explained more in detail by the mechanical rover package. Next slide, please. Thank you. Once all the samples that we want have been collected, the rover may enter the wayback mode. During this mode, which is quite similar to the travel mode, the rover gets back to the forensic lab to deliver the samples freshly collected and give them to the lab so all our payload equipment can analyze them properly. Now that the scenario of the mission is explained, Miguel will talk about his work concerning the thermal warp package.
Hello everyone, I'm Miguel, and as we previously mentioned, the lunar environment is very challenging and the thermal design is one of the main drivers for the success of the lunar mission. And here we are going to try to explain what are the steps we have followed to keep all the elements on the operational temperature range, which is the main requirement for the system. Usually it is between 0 and 40 degrees Celsius for the electric equipment, which is what we have taken as reference for the thermal design. At the beginning, you can see a representation of the rover with the elements of the thermal balance. And what we did is to divide it in 6 different thermal zones that you can see here. In between these zones, we installed 2 thermal isolation. One of these was a high thermal resistance material to cut the thermal conduction, and the other was the use of MLIs to cut radiation. So now the nodes are isolated from each other. As a result, nodes do not have thermal interaction with each other, and we can assume now the steady state condition. This helped us accelerate design iteration in the preliminary design phase. Next, we put all the electronics on the top, since it does not have a view factor to the lunar surface. Thus, it is relatively easy to design the thermal balance, only taking into account for solar radiation, QS, heat generated from onboard electronics, QE, and radiation emitted back to outer space, QSP. Also, the top surface receives no heat from lunar surface. Because of that, it can be considered the perfect place to have the radiator, since it will avoid the lunar radiation factors. Next step is to size the radiator. The radiator should be sized for the worst condition. So when the sun is heating completely to the rover, and the radiator depends on the temperature, which is what we have selected first, as you can see here. It is important to select a value lower than the upper limit, in our case 40 Celsius, because inside the rover will exist a gradient of temperature, but the heat pips that we are going to install can more or less uniform it. Also, the radiator depends on the emissivity of the material that is made, and indirectly also depends on the absorbability because of the equilibrium previously mentioned. To see if the lunar dust was going to have a real impact on the radiator, we did a simulation for 7 days with the typical values for other missions and extrapolated to 7 days. Because after 7 days is where we have our worst case. But the results were around 0.14 degrees Celsius, so almost negligible. And the reason that we took 7 days is that we consider that the rover is going to be clean in the lander every night. But with the typical values for optical solar reflector, at the end of life, we have some problems if we go with the arm as internal equipment. As you can see here, we need more area than the complete top surface. Difficult to get solar radiation because the absorbability of OSR is very low, which would mean a lot of power usage just to heat the rover in the coldest hours. And the last one that is related with the previous one, because in the coldest hours, we don't want to be radiating the same quantity as in the hottest conditions. The solution is to install a louver. And here you can see some pictures when we were defining it. And for the louver, we are going to use black paint on it because it has an equilibrium between absorbability and emissivity. We decided to divide the radiator in 13 independent zones that can be closed or open independently. And as you can see here, in the following diagram, we divided thermically the emission in 12 zones using the degree that the sun has with respect with the rover, as you can see in the little diagram. We consider that the distance between the sun and the moon is large enough that the solar flux is essentially a constant wall of heat coming towards rover surface. But the sun positions in relation to the lunar surface is important. To solve that, we need to use a simple trigonometry relation. The inputs we have to face the dissipation and maintain the thermal equilibrium are QE for internal power generated by the onboard equipment heat, and this depends on the mode we are. The louver for the area that the radiator is covered, and the Q, which is the power added by the electric heaters. Here you can see an example for the less and the more power demanded mode and how the same quantity of heat radiated is supplied to reach the equilibrium in percentage. For the exceptional cases that have not been considered, like for example, the inclination of the rover, and also to mitigate the peaks we can suffer and make the temperature more stable, we have to install a phase change material with the radiator and around the electric equipment and also around the samples container. For this, we have selected this material. We have that really good characteristic. It's called phosphonium chloride, but the only problem that it has is that it is toxic. So we have to be very careful with it. We have another option just in case, like N-hexadecane. And as you can see in these pictures from the spacecraft thermal control handbook by Gilmore, that are very representative that what I have talked here. Also, to finish, you might be asking what happens with the external equipment. Well, the procedure is basically the same as we have worked before, but with one difference, and it is for the motors we have in the wheels. We have to consider the performance because part of the power is converted in kinetic energy and part in heat, which is what we have to focus in this thermal system. And we have to size the radiator for the worst conditions and install the louver and PCM. And now you will see the different configurations for the rover.
Thank you, Miguel. Good morning, everyone. My name is Adrian. And so far we are talking about this rover, but you haven't seen it yet. So let me introduce you to some of the different configuration that the rover has. So the first one is the Earth-Moon travel configuration. So in this configuration, every equipment of the rover is stowed to provide the best possible mechanical strength to bear the loads during the liftoff and the landing on the moon. The rover will be restrained to the lander with single-use mechanisms and pins. The locomotion system, so the wheels and the suspension system, might need to be stowed during this mode, and in this case, they will be deployed only after the landing. Then we have the hibernation configuration. So as Valentin presented before, this is when the rover is inside the lander during the nights, the mornings, and the evenings. In this configuration, the mast, the drill, and the antennas will be stowed. They will not be used during this mode. And the solar array might be stowed if the lander requires it to if the lander requires it, or it can also be used to lower the thermal transfers and keep the rover's heat. The locomotion system will keep deployed, and it will never be stowed again. Then the travel configuration, where when the rover needs to travel from a point to another, for example, from the lander to the crater. Here on the science equipment, so the drill and the arm are going to be stowed as they will not be used. And of course, the solar arrays, masts, and antennas will be deployed. Finally, the drilling configuration, when the rover is in a crater to drill a meteorite, every mechanism of the rover will be used during this mode. So the drill and arm will be deployed to collect and store the meteorite sample. During the drilling process, the arm holds the sample container near the drill while it collects dust. For more stability and precision, the sample container can be fixed to the drill during the process. So here we have an animation of the rover's deployment. So after the landing, in the Earth-Moon configuration that you can see here, the rover deploys all the necessary equipment. And it ends in the travel configuration here. So then when it arrives in the crater, it deploys its drill. And then the robotic arm to be able to operate and move the container box. So let me now present some of the general configuration on its main equipment. So first we have the mast cam and supercam that have been introduced before that are on top of the mast. They allow us to have a panoramic view of the rover to analyze the ground and the craters, and they can also be used for obstacle detection. Then we have the RIMFAX that was presented as well, which scans the area to find the meteorites. We need to drill up to 10 meters deep in the ground. It's placed around 60 centimeters above the ground. Then the hazard cameras allow the operator to have better view of the ground level and to detect obstacles. It removes the potential dead angle that the cameras on the mast might have. So on the payload part, the regolith drill can drill up to 1 meter deep in the ground to collect the sample dust. It's deployed with an arm that can change its position horizontally and vertically using 2 motors. The sample container will store the dust that is collected by the drill, and it can be placed inside the lander. Inside the rover, sorry, for preliminary analysis, and then inside the forensic lab for the detailed analysis. The robotic arm is used to move the container between the drill, the rover, and the lab. It can also be used for the interaction with other missions payload. The worker bogie system has been used to allow the rover to be stable in any case and to climb obstacles that are up to 20 centimeters, so around the diameter of the wheel. And finally, the low gain antenna will be retractable, so it can reach up to 2 meters to communicate with the lander, even when the rover is inside a crater that can be up to 2 meters deep and can communicate up to a distance of 4.5 kilometers. The top surface of the rover body will be used, as Miguel explained it before, for radiators and louvers to keep the rover at acceptable temperature. So now I'm going to speak about the different sizes of the rover. So the rover will have up to 1.7 meters squared of solar arrays to generate around 200 watts of power for the rover equipment during its different modes. And the minimum volume of the rover is 2 meter cubes. It's when the rover is in the Earth mode configuration, so when everything is stowed. The drilling configuration has the highest volume, and it reaches up to 2.5 meters long, 1.8 meters wide, and 1.5 meters high. The Earth Moon configuration, as I said, has the lowest volume and is 1.5 meter long, 1.3 meter wide, and less than 1 meter high. Finally, the total mass of the rover still has to be determined. Thank you.
Okay, so now we have a configuration for our rover. So I will introduce about the mechanisms and the structure of this one. And so my two main questions are, what are the needs for the rover and for the mechanisms, and what are the hurdles we have to face? So first, for the need. So we need to have a solar array deployment, because without the solar array, we won't be powered. We need a mass deployment system so that we can see everywhere around our rover. We have to be able to drive to go to the crater and to move inside the crater. And we need absolutely a sampling and storing system so that we can get samples and store them once we collect them. For the challenges, as my different team members said, we have problem with temperature, the regoliths that can get inside the joints for the mechanisms. It's very dangerous. The lubricant choice is very important, because we don't want to have anything, we don't want to outgas, and like the material material of the mechanism shouldn't outgas also, because we need to remember we are in space, and yeah, we don't want to outgas. And finally, the launch and landing environments that are pretty harsh with like high vibration, and we never know what's going to happen. So now let's have a look at the different mechanisms, starting by the most important one, which is, of course, the solar array deployment. So it's very key to the mission, because it will power our rover. So it cannot fail, because if we have no solar array, we have no power. If we have no power, we have no mission. If we have no mission, we have no mission. So it shall not fail. It's very important. So for that reason, we choose to have redundant mechanisms that can work independently, to avoid that a single event failure would lead to a total end of the entire mission. And now, so once we can be powered, we need to think about the locomotion, so the wheel and the motor that will drive the rover. So on one side, we need to drive. So what are the objectives? We need to drive to the crater. We need to enter, exit in, out of the crater, but also out the lander. So the key driver are given by the time we allocate the rover, and that leads us to have a travel speed of 180 meters an hour. But beside of the speed, we need to be able to fight against the gravity, and especially be able to move and maintain our rover in a slope of 33 degrees, which is quite high on Earth. But when you go inside a lunar crater at the edge, the slope is very high. So we need to sustain of that. We need also to be able to maneuver, to make the mapping of the crater once we are inside, and position exactly the drill where we want to have. And all of that we want to keep in the system in our power budget, which is between 90 watts for cruise traveling, and 120 watts when we are like in a slope thing. So that drives us to have a wheel diameter of 20 centimeters, and a motor reduction to 200, a ratio of 200, meaning that we can have a balance between the speed and the torque of the motors, keeping good mobility by adding motors on the wheel, like to turn. So now we can move. We want to be able to manipulate the samples, and so let me tell you about the sample story. So the sample story, First we drill from the samples, and these samples of the meteorite will get into a sample box, which can contain up to 5 samples, different samples from tube. and this box will be put inside the rover in a specific space to be safely for the safe travel using the robotic arm. Then we can travel to another crater, and then to repeat the thing, and then going back to the lander and go inside the lab and put the sample box into the lab so that some analysis can be made and conducted. Yeah. So now the sample box on the next slide. So for the sample box design, we selected to have a one unit CubeSat format because it's standard. So meaning if it's standard, as we are sharing the drive and there are other payloads in the lander, it's important for us to be able to, if we have this standard shape, the robotic arm can also move other payloads. And for the inside the box, we selected to have 5 tubes, 5 possible different samples, as the sample volume is 72 centimeters squared. And so now we will look at the robotic arm and how it is designed to move, to handle the different sample on the next slide. So for the robotic arm, so we will manipulate the sample box using a hand, which has 2 fingers that will press on the both sides of the box so that we can, with friction, we can really manipulate it. And so we selected material like for both the box and the hands, the fingers, aluminum alloy, so that we can have really a good friction, a correct friction to minimize the power needed. And for the robotic arm, as we want to do some translation to take the sample box back from the drill and put it back in the rover, and same to put it in the lab, we need absolutely 3 rotation axes, and a 4th degree of freedom is needed so that we can have left and right rotation. And because the lab is on the side of the rover when we are in the lander, so we need to have this right and left possibility. And finally, like we are in the, we need to respect the power budgets given. And so, yeah, this way the robotic arm is capable of transferring the sample box into the lab so that analysis can be performed by the payload team.
Hello, hi. I'm Vibish, and working with Akshay from the payload team. So with the requirements with the science requirements that Akshay had given us, and the budget requirements that we have as part of our project, we had come up with few of the payload instruments that are going to be on board the rover. So we've selected 4 instruments that will be going on the rover. The first one will be the Icebreaker to 3rd gen, which will be the regolith drill. And as you all know, the other 3 instruments have been used in the recent NASA Perseverance rover, as you're all probably familiar with it. The scope of our project, it's so to design specific payload instruments kind of outside our scope of this project. So we're kind of using these instruments in our kind of situation to see when these payload instruments will operate and at what time. Next slide, please. So we've got the Mastcam Z, which is the camera equipment on the mast, which will be used during the identification mode, which will characterize the overall landscape geomorphology and its processes. And this will decide, it will analyze the crater and will decide if it's feasible for the rover to enter. These cameras can also document dynamic processes and events via video, and as well as activities related to driving, sampling, and caching, and contribute to the rover navigation and target selection for investigations via the caching system. And this will be operated at all times. Now we go to the next instrument, which is the RIMFAX. We have which is the electromagnetic sounder, which will be used to analyze the subsurface using the ground penetrating radar. Now this, once entering the crater, this instrument can be used to identify if there's any apparent change in density to locate some points of interest. So the RIMFAX scientists can analyze the radar data from Moon to identify underground structures and materials by their unique radar reflection. So the speed at which the radar signal travels is dependent upon the composition of the material being penetrated, and the depth of the target is based upon the amount of time it takes for the radar signal to reflect back to the unit's antenna. So this instrument will also be operating at all times, and it will measure every 10 centimeter of the rover trajectory. Now we move on to the next instrument, which is the SuperCam, which will examine the rocks and soil with a camera, laser, and spectrometer. So it's got like 4 different types of spectroscopic methods. It's got the Raman, visible, and infrared. It's also got a remote imaging system, camera system, and also the laser-induced breakdown spectroscopy, which is one of the key methods that's been used, which is made it advantageous over the other spectrometers. And these kind of this SuperCam will be placed on the mast, and it does not need to be essentially placed on the robotic arm like in the other rovers, as it can identify the chemical and mineral makeup of targets from a distance of more than 7 meters. So if we go to the next slide, we'd be able to see the criteria to drill inside the crater. So now we've got 4 cases, which is kind of an additional information of what the Valenton, my teammate Valenton was on during the operational modes. So case 1, we've got where the SuperCam and InFrax both detects that there is something in that zone. So then we can start drilling in these high concentration zones given by the chemical maps from the SuperCam. And now there might be a case where the SuperCam detects some chemical signatures and the RIMFAX does not detect. It could be maybe because of high impact velocities. Maybe the meteoritic material could be vaporized due to high velocities, but there could be a chance that they could somewhere be underneath the subsurface. So there could be a chance where there'd be chemical signatures of these in the surface. We could still go looking for these high concentration zones of these meteoritic content. Now, where we have a case where the SuperCam goes undetected and the RIMFAX detects, there are some cases where, for example, my teammate Akshay was talking about the terrestrial meteoroids. So these meteoroids can be below the surface up to like 10 meters, and these can be detected with the apparent change in the geological structures using the RIMFAX. And now we come to the 4th case where we'll move to the next crater. This will be the only case where when both of these instruments go undetected, we'll move to the next crater to do the sample collection. Now, the next slide. So now we have the regolith drill, which will be used for drilling and sampling operations inside the crater once we decide where to drill. Now we've got, so this drill it has a penetration depth of about 1 meter, and it also has a sampling system that will collect when we drill, so it will collect the last 15 centimeter of the sample, and it will be transferred into a sample container inside the rover, which has a volume of about 72 centimeter cube per sample tube. So we can easily fit it inside the sample container and take it to our lunar laboratory, which will be based in the lander for further spectroscopic analysis. Now, we are assuming that we will have the lander, we'll have the forensic meteor lab inside the lander. So we have given a list of suggested equipments that could be used for further analysis once we get back to the lander. So the next slides will describe that. So we've got the APXS, the Moss power spectrometer, Pixel, FOCI-POL and FOCI-MAT, which is a thin section preparation system, and a polarization microscope. Next slide. So we've got APXS and Moss power spectrometer inside the lander, which will be placed in contact with the samples, and will expose the material to alpha particles and X-rays emitted during the radioactive decay of the element curium. So most of these experiments, a preliminary analysis of both these instruments could take about 1 to 2 hours, but we can get further analysis within a few hours of operation. So the next slide, please. we've got the most power spectrometer, as I was discussing about. So these both go hand in hand, where the APXS provides the elemental composition for the target, and the most power spectrometer provides the mineralogical composition, including the ion ratios, so that the concentration of these ion containing minerals can be detected with high accuracy in this kind of spectrometer. So these these ion bearing minerals like olivine, and these quantitative measurement of the distribution of these ion among these ion bearing phases, the relative proportions of iron in olivine, pyroxenes, etc., can give us more solid information on these samples. There's another few equipments which my teammate Akshay will be describing in detail. But for now, I'm done. Thank you for listening to me. And we would like some good feedback from all of you towards the end of our presentation. Thank you.
So the other instrument that we are using is also a spectrometer, and the previous ones that are the MOSBAR and APXS are kind of redundant ones, which we'll be using just to verify the quantities of each element in it. So the Pixel was previously used on the Curiosity mission. It was initially aimed to be used on the rover, but because of the new arrival of the SuperCam, we placed it on the lunar laboratory. So this weighs around like 7 kilograms, and it is a higher sensitivity equipment than both APXS and MOSBAR spectrometer, and it will be able to detect a lot of minerals, and it can accurately give how much concentration of each element is present in the given sample, and it takes a detailed analysis within like 2 minutes. And this is one of the most important equipment in the lunar laboratory, which will be used to categorize what kind of meteorite that we have in our hand. Can you go to the next slide? And this is the thin section preparation system. So basically, this section, I mean, this equipment is probably the ones that weigh the most in the entire project, like individually. But I mean, ironically, they are not that important compared to the other ones. So this one, what it does is that this is a grinding and polishing. There are 2 instruments in it. One of them grinds and polishes the sample. The other one latches them. So the forcipole, which is in the bottom, is the polishing machine, and it makes the sample into very thin sections, like 25 to 35 micrometer. And the forcimat that is shown above, what it does is that it latches them in between 2 polarized filters, and they are of the dimension that is shown below. So this includes the thickness of the polarized filters, but the actual sample itself will be like 25 to 35 micrometers. Next slide. So for analyzing the sample, I've selected this IPP902 microscope, basically because all the 3 instruments, I mean, all the previous 2 instruments and these go together since they are made by the same manufacturer. All are completely automatic, and this is a petrographic camera, a petrographic microscope, and it has a 3.6 watts illumination in it, and ironically, it has a 50,000 hours of lifetime, which I don't think we would be needing, but anyway. So, and it has like 3 types of focusing, which it can do: the coarse, and the coaxial and fine focusing system, and it can have different brightness levels using its adjustable polarizing filter. It can tilt it up to 0 to 90 degrees. So, and it has a magnification of 500 times, and all these samples will be analyzed, and these images will be sent back to Earth to decide whether or not these samples are worth enough to recover back to Earth to do further analysis on them. So that concludes my presentation on this lunar laboratory.
So hello, I'm Jorge. I'm in charge of the aids and communication systems of the rover. Let's now take a look into how the rover thinks. Well, in this design of this subsystem, the OBD8 subsystem, the main requirements that we want to achieve were to build a rover able to manage the functionalities of the different operational modes that my teammates explained before, able to operate half autonomously, that is, to have an operation which is autonomous with possible interruptions and confirmation from ground control to go from one mode to another. Also, to operate commands and generate the corresponding telemetry, and the most important one, to be reliable and fault tolerant in order to work in the Moon environment. So after trade-off analysis, taking into account the computational resource estimation, flight heritage, and physical constraints, as well as the principle of using components of the self to reduce development cost, the brain of the rover selected is the RAD 750 Space VPX single onboard computer developed by Base Systems. You will be, I hope you will surprise as me to know that this computer uses a processor quite similar to the one from an Apple computer from 1988. Nonetheless, this radiation hardened computer satisfies the needs of the mission with radiation protection up to 100 kilorats. It can deal with up to 500 mega instructions per second with a lower consumption and one of the wider temperature range in the market. It also has enough radiation hardened memory for our purpose in order to store code and execution data, and also to store scientific data with a non-volatile memory. In order to guarantee the fault tolerant aspect, two onboard computers like this are going to be placed on the rover. They are not working at the same time, but in the case that the main one has a critical failure, the other one will take control of the situation. Next slide, please. The structure of the system will follow this double federated bus architecture using firstly Spacewire bus, in which design and conception ESA was involved, developed to manage data from the scientific payload and cameras with a data rate allowed between 2 megabytes and 400 megabytes. For the rest of the elements, including the guidance and navigation unit, which has been doubled for redundancy and reliability purpose, the military bus is there to manage lower data rate that the Spacewire is not designed for. Why this architecture? Well, this architecture provides more reliability than point-to-point ones in a way that if a single node fails, the overall subsystem can survive. Next slide, please. All right. Now, once we know the brain of the rover, let's take an insight in the ears and the mouth as well. The communication subsystem must enable us to get the scientific data, to receive the telemetry, and to provide the commands that I talked about before, and to guarantee the availability of the rover in any case ground control requires it. Next slide, please. How do we talk to the rover? Well, there were several key aspects that influence more than others in the speaking and hearing ability, such as the power limitation, the fact that the lander could operate at the moon as a lunar relay, the lack of atmosphere effects that interacts with the radio frequency waves back at the Earth, and also the lunar surface effects. At the right side of the slide, you can see a summary of the data rates generated by the equipment that we carry on in the rover and also in the lab. Higher data rate transmissions, such as the standard for video broadcasts stated by the Consultative Committee of Space Data Systems, demands more energy, as well as longer distance too. Then the selected architecture of the communications links is the one that you can see in the middle. 3 nodes, the lander, the rover, and the ground station of the Earth, with 2 links, the proximity link at the moon and the Earth lander link. Well, now the proximity link. This link is allocated in the ultra-high frequency band. As you can see at the right graph, this band has lower surface path losses than higher bands as the S band. And it uses a low gain dipole antenna that with a power consumption of the overall system of 10 watts can establish direct communication with the lander in the 4.5 kilometer range, switchable for our mission objectives. The point of using this omnidirectional low gain antenna is to allow the rover to communicate with the lander independently of the orientation of the vehicle with respect to the lander, avoiding also pointing losses and the use of mechanisms to orientate the antenna. Following the CCSDS standards, it uses a quadrature phase shift key modulation and a coding scheme that requires relatively low energy per noise ratio for the maximum data rate of 45 megabits per second. Well, and for the Earth lander link, since the design of the lander is responsibility of ESA, we can only suggest the design of this part of the system. Following the state of art and future trends, these are our suggestions. The communication can be achieved in the X-band, avoiding this way bandwidth constraints in lower bands. For the Earth-Moon distance calculations that I made, so that with a 1.5 meter square phased array antenna that could be placed on the top of the rover, and also with the support of the DSN or ESA Deep Space Network, the communications between the lander and the Earth can be done. Also, due to the fact that we are probably sharing the Moon with many other projects, we're required to have code division and multiple access to the lander blade to avoid time and frequency constraints. Finally, the lander also must be equipped with the same omnidirectional receptor on its top to guarantee the communication with the rover. Thank you so much.
So regarding the rover's autonomy, we decided that some operations such as path planning, self-localization, and obstacle detection and avoidance will be directly handled by the rover autonomously. So the rover will do that using a mix of algorithms, cameras, and sensors. But the ground control will be deciding on the transitions between the modes. Valentin mentioned previously, and validating the path planned by the algorithms. Also, the craters that will be inspected will be also validated by a science team on the ground. And also the rover, once the rover arrives to one crater, the ground will take control and try to enter the crater by spiraling it and searching for the meteorite. Next slide, please. So to ensure the autonomy requirement, we developed several algorithms. The first one is to detect obstacles and avoid them using a mix of algorithm and sensors, precisely infrared sensors. So first of all, the sensors will be placed on the rover to cover 180 degrees and create some sort of a sensitivity bubble. So this bubble's shape and size will dynamically adjust depending on the distance traveled and the sensor's range. Also, the sensors will be uniformly distributed on the rover, and the readings can be represented in polar diagram, as we can see in the photo on the right. So after the goal is defined from the previous algorithm, the rover will start moving forward to it. So once an obstacle is detected through the sensitivity bubble I previously defined, the rover will rebound and find the new direction with the lowest density of obstacles based on the sensor's reading. And the rover will continue moving to the new path until a new obstacle is detected or the goal is reached. So the second algorithm was developed by Akshay. So this one is also for path planning, but the role of this one is to find the optimal path from the lander to different craters, the Neliotas one or the other ones we will be inspecting. So this algorithm has for inputs a database that we constructed based on the LRO. So this database contains information about the craters like depth, diameters, and distance from the lander. Also, we have as input data from Neliota. So that has an additional information about the mass of the meteorite. So based on these database, the algorithm will decide on the 5 most suitable craters that can be visited, inspected, and the scientific part performed within just one lunar day. Next slide, please. So here we have an example of the algorithm executed in MATLAB and having for this scenario, having 4 craters that can be visited. So the rover will be going back and forth from the lander to inspect each of these craters and to search for meteorite for it. So yeah, that's it.
Hi, everyone. Very good morning to you all back in Houston. I'm Harry, and I'm in charge of the power subsystem in our mission. So I made up the power budgets. I took inputs from different work packages, and I came up with the power budget. I decided what components we're going to use. I decided the size of the solar arrays and everything, and now I will be presenting my slides now. So first of all, it was decided that we're going to restrict the rover operations only to lunar day. So that means that it works for 14 days when there's sunlight on the moon, and for the other 14, it stays inside the lander. So the absence of RTG means that the power required to heat up the rover during cold lunar nights, which are really cold at minus 183 degree centigrade, would increase the power consumption to very high amounts. So the total energy required for the greatest single load would be about 338 kilowatts for 14 days, which gives a battery energy drain at 246.4 kilowatts at a discharge efficiency of 0.96. So, using all these calculations, the main thing is that the size of the battery that we would require to power up the rover without the RTGs would be about 5,000 kilograms, which is 10 times the size of the mass of the rover. So that's kind of impossible. Next slide, please. All right, so this right here is a kebab truck, and this kebab truck weighs about 3,500 kilograms. So according to the previous calculations, we would need a battery which is 1.4 times the size of this kebab truck on the lunar surface to power it up without using the RTGs for 14 days. So as you know, we cannot send kebab trucks on the lunar surface yet, but one day we will. Next slide. So these are the power budgets that I made in terms of the operational modes. So we have the yellow ones, which are classified as active modes. We have the blue ones, the dark blue ones, sorry, which are the semi-active modes. And then we have hibernation and safe mode, which are idle modes. So we have the minimum power, we have the maximum power, and the average power. So I've highlighted in red the collecting mode, which is essentially the basis of operation of our mission, because our job is to collect meteoroids on the moon. So for collecting mode, we would require a maximum power of about 182 watts with an average of 168 watts. And on the next slide, we will see, we will break it down, the collecting mode into different subsystems, right? So this mode was rated the highest in terms of power consumption. And due to the payload team deciding that the drill would not require 300 watts, it could be done in 100 watts. This significantly helped us to bring down the power budget of the collecting mode and to reduce the size of the solar array, which was quite important for the configurations and for the mechanical team. So this mode is the most important operational mode as it directly corresponds to mission requirements. And so the subsystems that we were going to be using on the collecting mode is communications, which has a power range of 10 to 12 watts for lunar communications. We have the obedient system, which is 26 to 30 watts, including all of the sensors, the IMU, the gyroscopes, all of those things. And we have the camera, which is going to be using 18 to 20 watts, which I've assumed as a standard value for camera. And then we have the drill, which is 100 watts to about 120 watts. This information was obtained from the payload team, of course. And in the next slide, we have the calculation that I did for the solar array and battery sizing without taking too much time and going into too much details on the numbers. I can say that the important numbers in this calculation are the solar array area required, which would be 1.615 meters square, and the battery mass, which is 6.22 kilograms. However, I suggest that there are situations related to power that we cannot see. So for instance, if a cell fails, or for some problem happens and we can't use all of the power from the solar array, I think our battery should have a margin. And for that, I suggest that we use an additional 200 watt hour to get it up to 822 watt hour capacity, which would be more than enough for our mission. Next slide. Right, so this is a graph that I made, an operational cycle in which I'm assuming the operations for 24 hours on the surface. And as you can see, the maximum discharge from the battery is about at 400 watt hours, and all of our power consumption, which can be seen in the blue dots, are below the maximum battery discharge. So I think we are okay in terms of power. Next. So the assumptions and the margins that we're taking is that at one point, no two modes shall be operating simultaneously, which makes sense because we're going to be smoothly transitioning from one mode to the other. And then the collecting phase is assumed to go on for 2 hours and 24-hour cycle. I have also assumed a 10% systems margin for the charging of the battery loads, and an 8-watt additional power was assumed for essential subsystems when power required for maximum daytime loads was being calculated. On the left, you can see the kind of battery that I propose to use. These are from Saft battery corporations in France, and you can see the dimensions and the sizing of the individual components on the left. And on the next slide, on the next slide, I've just explained my assumptions and margins, and I think we can skip past this and go to the next slide. These are the constants that I've assumed for all of the operations. So these are obtained from a book that we have called SMAD, which is for our Space Systems Engineering course. And I've used these values from there to make necessary assumptions for the constants, and then use them in my formulas for calculating the power budget. And on the next slide, we have the failure modes for power. So 1 means system critical, and 2 means mission critical. So when it comes to the major components, solar array and then battery power. So for solar array, if we have a single failure, it means a partial power loss, and our response would be battery backup. So the criticality is system critical. But if there's a multiple failure on the solar array, then we have a complete loss of power from the solar array, and we have to go directly to battery backup. This would be mission critical, as we would not be able to accomplish all of the things that we hope to achieve. And for the battery power, we have single failure, multiple failure, charging problems, and overheating. And the effects of these are partial power loss and then substantial power loss. For charging problems, we have reduced capacity, operational hindrance, and for overheating, we have risk to equipment. So for partial power loss, for the battery backup, actually the battery that we're using is already a backup to the solar array, so we don't have any response in case there is a partial power loss. But in case of a higher power loss, we will need to be very selective about our power consumption. Maybe some of the payload equipment that we are using and we can do without it, we will have to shut them off. And for if we have a reduced capacity, then we go back to selective operational modes. In case of something that's system critical, we have a safe mode, which will prevent our mission from our rover from crashing. Then we have overheating, which can be fixed with insulation, cooling, which we have the Miguel working on the thermal subsystems for that. So that's good. Next slide. So I'm done.
All right, guys.
Thank you for my thank you for that.
All right, guys. This is me, Flavine, again. I would like to talk to you quickly about how we manage the risk for this mission. So first of all, the idea that we started to use is this risk management process that you can see on the right. So it works in 4 steps. First of all, defining what the risk management process is, how we're going to manage and implement it. Second step that repeats is the identifying and assessing the risk. Then we have to decide and act upon those risks. And finally, we want to monitor, communicate, and accept those risks and make some decisions based on them. So obviously, this is an iterative process. Multiple times throughout the mission, we can make some decisions that will impact all of the other work packages, change how everything works, and then again, we have to assess the risks again. So first of all, we have to, as I said, the step is to identify and assess the risks. So we classify the risks in 2 types. So the project's risks, which are risks related to the completion of the project, whereas we also have the mission risk that are the risks related to that threaten the completion of the mission objective. So, for example, some project risk could be the communication failure between the team members or overrunning deadlines, etc., etc. Whereas some mission risks are some assumptions that are not actually being met, or some failures in the mechanisms, or the dust interfering with our operations a bit more than we expected it to. So to answer those risks, it's quite important to make some decisions during the project to diminish them as much as possible. So first of all, this slide is all about making the decision and acting on top of those risks, which is actually the step 3 of the risk management process. Some examples here of how the risks were mitigated are shown here. So for example, the redundancy, such as having multiple payload equipment to use for the mapping, multiple samples being collected, multiple cameras being available, but also for project risks, for example, we have the idea of setting multiple places to access our files, multiple ways of communicating. We also obviously use margins, as Harry mentioned very well earlier during his power package, but also for so many other things such as the OBDH and the communication budget, where we overestimate what we want to do. Najwa and Valentin mentioned earlier the ground control confirmation. Because the rover is pretty much entirely autonomous, we wanted to include the ground control in the decision taken. But we also wanted to avoid having a technician's time being wasted by having the rover being remote controlled. So we felt that the best way would be to have the confirmation of ground control before certain actions. Another thing that we need to do, obviously, is to plan for the environment. It seems a bit obvious, but being prepared mitigates a lot of the risks. We're aware of the radiation, we're aware of the temperature, we're aware of the dust, and that means that we can plan around them and reduce those risks. And finally, the safe mode is the last way to answer the last step of the risk management process. So the safe mode here allows the rover to be constantly monitored. It allows it to communicate with the ground control at any time, should a problem arise, and even if it is very small. So the whole point of that safe mode relies on a monitoring process that works at all time. And it's based on sensors and multiple readings of the rover's activity. And whenever the monitoring process finds that something is amiss, it immediately starts going into the safe mode, where the data are saved, all the power is deferred to thermal, communication, and cameras and OBDH. And from then on, we can actually assess, identify and isolate the problem, and see if we have any known resolution. So that means that the safe mode relies on having a library of known problems and known resolutions that work with them. This means that we avoid relying on the ground control for any and every single issue. This saves time both on the technicians on the ground, but also for the rover, which is quite a good option. Obviously, in case of a problem that has no known resolution, we can still report to the status to the ground control and request a solution to be decided. In all scenarios anyway, the problem and its resolution are documented, and then we can go back to our original mode. So obviously this whole mission works on some assumptions. For example, we assume that the lander will survive the night in order to protect us. We also assume, for example, that the lander will be able to clean the rover, that it will have enough energy to power the lab and power itself during the night, and that we will be allowed to use the cameras on board of the lander in case, like during the landing, in order to map the area. Assumptions are critical to our mission, but thankfully we also have some sort of backup scenarios in case those don't work. In the case of the lander not surviving the night, we can still function as, for a single lunar day, we'll still be able to collect samples and we'll still be able to analyze them. Obviously, that means that our mission only lasts 14 days instead of 180 days. As for the lander not being able to giving us the use of its camera, we have already several mapping accessible that we can use, several maps of the moon that are already accessible online, and also we are using cameras on our rover that will be able to already make some sort of maps. Finally, we are also hoping that the mission will still be able to run for several cycles, even if we're not able to clean the dust off of the rover. It obviously means that it's more likely that it will die sooner than expected, but it can still do multiple night and day cycles. And what we're hoping is that we will be able to actually have a lab on board that can analyze our samples. But in case it doesn't work, we're already collecting enough data with the rover thanks to the payload equipment on board. Finally, I also want to talk about the showstoppers that we had during our mission. Unfortunately, obviously, as you all may be aware, group projects and just generally any project doesn't work very smoothly, and we had a lot of runs into walls, such as, for example, we had some ideas for the design of the Hunter being like balls, as you may have seen in the latest Star Wars movies and stuff like that. And that caused some problem with mainly the power consumption. We also considered carrying the lab on board, but that was massive and the battery was not going to be able to be enough for that. We considered using an orbiter for the communication and also for mapping the areas, but that is extremely expensive. And as you can expect, that's a whole other group project that we didn't really have the time to work on. We considered directly with Earth instead of relaying through the lander, but that makes the communication budget very high, that makes it extremely power hungry, and just generally it makes it extremely uncertain. As you can be aware, space is a bit difficult to work with when you're sending data over a very long distance. We considered using multiple rovers, but generally, again, that was always a problem with the survivability of those rovers, even if we were to carry smaller ones, and just generally as well, the battery size, the space survivability of those was not really useful. All right, well, that is it for us. Thank you very much, everyone, for listening to us. I hope you enjoyed it.
Oh, wow.
Question?
Thank you so much. Yes, there's definitely questions. And before we start asking questions, I just wanted to mention again that this program is recorded. We will post it on YouTube. I will also send the links to the recording. And for those that did not get a chance to listen sit through the whole presentation, I know that some have to leave. Josh is looking forward to watching the rest of the recording and provide you feedback. I do have a contact with Paul, so I will send. I jotted down some of the notes, comments as a feedback to you guys. But I want to compliment you. This was a great presentation, great approach, and I hope that in future I will see, if not the whole thing, but the elements of that implemented in the future lunar mission. Okay, with that, I did see that I think Gary wanted to ask something. Gary, go ahead.
Yes, as pointed out, the very critical, mission critical function is that deployment of the solar arrays. So I was wondering what mitigation steps are being implemented to make sure the success of that operation. For example, what's the mechanism for the deployment? Are we talking about stored energy or some motor? What safety factors are used, what testing, all the things being done to provide that assurance that that solar array is going to deploy.
Yeah, so for the solar array, so we plan to have motors first, but also like energy stored in springs that can be deployed like by activation to to have some redundancy on that.
Okay, on that stored energy, do you have some latch that has to operate to release and then the stored energy takes place?
So like it's the design is a kind of top level. So we have a design at the top level. So, but the idea is to have like just the mechanisms that's release the energy from the spring so that it deploys the solar array back up by the motors.
Okay, so what is that causes that release? I'm sorry, I didn't follow.
It would be like something like we talked about a servo motor or something like that, or electronic, something electronic.
electronic, or, you know, one thing one could consider is something that you overheat and melts, that momentarily overheats and melts and releases or something. There's probably several ways. One, of course, you'll want to make sure that whatever it is very simple and robust. The other thing is, of course, there's the command involved to do whatever you're talking about. So is that done by the onboard PC through a program, autonomous program, or do you have a backup ground command to perform that function?
So like, I'll probably be able to help a bit more here. So we actually did do a bit more of a breakdown of different modes. So the first step was, it was whether we wanted to have the solar panels fold back up when we went on board the lander again, because we actually realized that after doing it, that the actual size of the rover wouldn't be a lot smaller. And Hadrian, who I was talking with at the time, suggested that he felt that actually having a mechanism that would close up again would be quite risky. And originally, when we were looking at the design, we were looking how it would initially pack up and fold out. And he did actually discuss the mechanism with me, but at the time we were still working at the base level of the design. We weren't looking directly at all the mechanisms. So yeah, that was that. We haven't really looked at that level of mechanisms. When we started this project initially, we ran into a lot of big issues, and it meant that our design phase actually started about 3/4 of the way into the project, and it meant that the more detailed design we didn't get an opportunity to do, because me and Flavin were kind of the project leaders, and we started redoing the project, and then I got the coronavirus, which meant that I was ill for about 3 weeks, and then the group had to make a lot of progress very quickly. So when it came to the more detailed designs, those kind of mechanisms have got lost in the process.
Okay, very good. So yeah, you might want to, you know, as far as that risk, you know, at the tail end, you had, oh, by the way, I thought this was an excellent presentation. And I also want to compliment the group on it being a team operation and letting everybody participate for their areas of expertise. The one thing you might want to add to in the risk discussion that you had at the last is a little bit more about the mitigation of that solar array deployment, because as you pointed out early on, if that doesn't happen, then nothing happens later. So to provide, you know, the program manager or whatever assurances that a lot of things have been done to minimize that risk. Because that, in looking over everything, that seemed to be the most critical point to provide some focus on. But I want to compliment the group overall. I thought it's a very excellent group, and I like the teamwork.
Thank you very much, Kerry, for these comments. And we will have a look more detail on this, because yeah, it's clearly the point we should make sure it works well. So yeah, also thank you very much, Gary.
You're quite welcome. I'm wearing my Oklahoma State orange shirt because we're going to be playing the University of Texas today for the Big 12 championship in basketball. So that's a big deal.
The best.
I'm sorry, Gary. I support the University of Texas.
See, half our group is French and half of it's English, and England play France today in rugby. So,
okay.
So we got the same.
Let's hear basketball.
I have about three or four questions, and some of them are fundamental. And but first, I'd like to say I agree with Gary. This has been a very excellent presentation. Some of the acronyms needed to be defined, but that's okay. And you all did quite well. And the important thing was the teamwork was excellent here. So that's very good. One of my fundamental questions is you have a drill going down to get this meteorite in about 1 meter of regolith. And so when you go down to that point and you hit the meteorite, what you're going to do is drill into the meteorite, right? You don't have any way of picking up that meteorite. So you're going to drill up these bits and pieces and chips of the meteorite coming up. And so if I understand what's going on here, and then there's the problem of how do you filter out the regolith and the other materials that you drill up from the ground? You're going to bring up a lot of materials, but how do you find the chips in little pieces of meteorite that you are targeting? Can you address that?
Yeah, sorry. So just regarding the drill, so I did mention that we'll be picking the last 15 centimeters. So what we'll be collecting is not really meteoritic rock samples, but kind of like the fragments and dust, like you mentioned. And initially, this is something probably which I haven't mentioned, but first our target would be to analyze the regolith, the lunar regolith in general, and then calibrate it for our analysis inside the lander, so that we can differentiate between what the composition of the regolith is, and if any meteorite content, what kind of specific chemical signatures that we could find in them, and then differentiate it to do further analysis. But that is sort of the top level idea that we have had.
Yeah, to complete, like on my slide, I did an animation of the dust that is the regolith that is going high. So I just showed the animation is quite not accurate, because first we have the regolith, but then it's the last 15 centimeter. So we don't take this part, and then we take only like the last 15 centimeter that should be meteorites, and that will be analyzed in the lab, and we can then distinct if it's regolith or not. Yeah.
Okay, I see. And the other question I had along with that is, how do you target and how do you get a target to hit that meteorite? First, you use this one instrument. I think it's called the Rimflex. You have on one side of the rover, and then on the other side of the rover, you have the drill and the supercam. So how do you know that the Rimflex is going to see the same thing that the drill is going to go after? It seems like it's displaced by the length of the rover, and that gives you a lot of air in going down with the drill, which doesn't have much air to hit the right target. So it just seems like it's a very a problem that's going to give you a miss a lot. And that goes along with another question I had, and that is, if you're serious about really putting this thing on the moon, wouldn't you have a very comprehensive validation test of it on the ground, Earth on the ground first? And let's say you have a team bury something out in an area that you have your test rover go out and dig and find it with another team that doesn't know where the first team buried the target. And so the rover team goes out and tries to find it. And then if it can find it, can it drill down and get it? So I think that whole validation testing has to be looked at before you are serious about launching this thing on the moon.
Oh yeah, definitely.
And like to comment on the Rimflex. So we use the Rimflex actually before trying to drill, because at the beginning we don't know where the asteroid is in the surface. So first we drive in a spiral in the crater, and so we analyze every single part of the crater, so that we really can have a map of the underground of the crater. And yeah, the payload team may know it better than me, but we can see the gradients in the structure in the ground. So, and then we align us, like knowing the map we did with the Rimflex, we align and drill at the point we think there is the meteorites. But the idea of the testing and two teams on Earth is very good, very great. Thank you.
Yep. And also thank you for the feedback. I think another thing we might need to consider is the location of these instruments. I think that you were on about, so their coverage area might be different, which could give us a possible error. That's something that it's just strike my head right now for, but it's something that we might need to consider as well in our analysis section. But that's something that's a great point, and we'd like to probably consider it.
Right. Mike, if I could add to that, when you asked us about the drill hitting the target to get to the meteoroid, and then we're gonna drill the bits up, and there's a problem with the accuracy. I think that's a wonderful point. But we were having this discussion about adding additional cameras to the underside of the rover, which could maybe operate in to get that accuracy and to find out the exact position of what we're drilling, where we're dropping the drill and all that. Because once we're drilling, we don't have that maneuverability. We can't move it around and target some other areas. So I think we're going to be using some additional cameras just to increase that accuracy.
Right, and I was going to ask about the SuperCam. Go ahead.
Sorry, I just wanted to add something that Paul mentioned, is that the main driver of the whole strategy around the crater was actually that we wanted to be as efficient as possible inside the crater, and we didn't want to miss any information. This is why we went for a RIMFAX analysis plus a SuperCam analysis, and so this way we can have like, let's say there is absolutely no meteorite material inside the crater, we still have really useful data of the crater. So for example, the whole geometry of it, that will be really useful for impact dynamics. So this way we can have finally some in situ data of this meteorite impact. And also, having the whole crater mapped by the RIMFAX will allow us first not to lose any information, and even though we don't find anything in the crater, we still have some knowledge about what's happening under the crater. So that was the strategy.
That's very good. Yeah, that's a good point, that you'll get a lot of information even if you don't hit the target. And I was also going to ask about the SuperCam. Did I understand that the SuperCam has some kind of X-ray feature so that you could see below the surface with a SuperCam, or
no?
That
was the RIMFAX that would go beneath the surface. So that's the subsurface radar, and SuperCam is more of a spectroscopic instrument, but it has also got like a remote imaging equipment that could also take pictures of these minerals that are on the surface for analysis. But so that's what I was on about. It's got different type of spectroscopic methods. So it's got the laser induced breakdown spectroscopy, which so then it's got also the Raman spectroscopy. It's got the visible and the high resolution color imaging. So it's got different modes for which each spectroscopic mechanism, they've got their own specifications and requirements, and according to the requirement, these will act upon. But the laser one is I think it's the upgrade from the ChemCam that they had on the Curiosity rover, if I'm not wrong, which has been what its advantages over the other spectrometers.
Okay, so it does not have any X-ray capability to see underneath the surface. It has a lot of capability to analyze the surface itself, but
yes,
not to go under, but not to see what's underneath the surface, like some kind of a metal detector or something like that.
No, unfortunately. So this only looks into the surface, and we have the RIMFAX. So which is why, if you can go on to the next slide, please. Yeah. So sorry, the next slide. The 64 slide number. Sorry, yeah. So that's where you have the criteria where we use both of these to see. So the only time we will move on to the next crater that is only when the SuperCam and RIMFAX go undetected. And even then, as Val mentioned, we'd be able to still get useful information on the crater dimensions, etc. So that was sort of the top level plan. Yes.
Okay, thank you.
Yes, thank you.
Paul, I had a comment about when you were introducing the approaches, and I recommend, I think on your slide it says that, or at least you were, I think it's slide before that maybe, or that cannot fail. So instead of cannot fail, you may want to mention must work. It's because it's impossible to test cannot fail, right? And when the must work is widely adopted within the industry, and then you can further elaborate that can be achieved by whatever approach you guys adopted, whether two-fold tolerance, design, and so on. Again, we know that things fail, mechanicals or any kind of other engineering approaches can fail, but it's how we go around the failures. Failures is the whole thing about must work design. That again in the risks, loss of mission was initially kind of overcome or passed over, but then one of you have covered that, so that's good. And Flavine, in the risk management, really nice. Want to compliment the process definition for risk management. You may want to add to the project risk. One of the major hurdles, I guess, is in addition to a schedule overrun risk, is the funding budget overrun. That is one of the main reasons a lot of programs are being canceled or have been canceled because of the budget overrun. So that particular risk, I think, warrants to be included in the major project risks.
That's a very good call. Thank you very much for your suggestion. I'm writing that down right now.
Yeah, and thanks for the must work. I will change that.
Okay. Otherwise, I really enjoyed you guys' presentation. It's definitely lots of work put into it. You can see by the result, and obviously with being a distributed team, that's what happens in the real missions. That we specifically on Gateway, we are very distributed. We work with various partners, with various module providers, and so on. So communication is the key. And there's a lot of question answer and going back and investigating certain ideas, and then they may not work. That is also one of the results. And so don't be afraid of something that you started as an initial idea and then it didn't work. That negative result is the result. It's still, that means you're not going toward that direction. You just have to redirect your thoughts and work on design to improve. Again, it's a real life experience. That's what we do as engineers and architects and designers of the real programs that are either flown, flying, or will be flying to space. So welcome to the real world. And I want to compliment you guys for a good, solid proposal. So I'm looking forward to the results of it. If anyone else have any questions, you're welcome to ask right now. I also wanted to mention that we hold SpaceGeekSpeak every Saturday. And if you are looking for any kind of feedback or questions to ask real engineers with lots of experience, this is the way to get that question answered pretty much almost instantly, or you can get a follow-up. Thank you for your appearance at SpaceGeekSpeak today. Any other?
I have one other comment, just a little comment, if I could squeeze it in, and that is on your risk management. In your risk management section, there is a mitigation technique that you might want to consider to add there. It's a kind of a collection of different things. You can accept, avoid, transfer, reduce, but you can also research. And in adding a research capability, that could also act to mitigate a risk which you can't find any other way to do it. And I found that many times if you do some research, you find that the risk can be shared or disappeared with another risk and then avoided or reduced that way. So you might want to consider a research class of mitigation.
Okay.
That's kind of a catch-all.
Thank you. I'll write that down and I'll look into it as well. Thank you very much.
Okay.
Svetlana, I have a question here, or I guess a comment. This is Wes Kelly. Invited in part because Paul Bowery and I had worked together during the summer, and I very much appreciate his contribution to our project. But I want to focus on the one that we just presented here, and it's been rather educational for me. It's been, I think it's an excellent job of integration and analysis, contributions from all the specific design areas. With the limited time I've got, I got a couple of comments, and that one is that based on my background, it's kind of a mix of astronautics and astrophysics, but the issue of identifying what is pertinent, I guess, in the search on the ground, the meteoritics, as it were. For instance, when we have something that hits the Earth, we have the atmosphere to mitigate its contact with the surface, so it's braked. And then the most profitable areas of, I guess, identifying meteor impacts have been on surfaces such as the Saharan Desert or the Antarctic plateaus, where they stand out. And then in contrast, we have the moon, which kind of cries out that we are all meteoritic in nature. So that's kind of mulling over that in the background of the talk in general, and couldn't resolve it in my own mind until finally I just thought of something. And that is that this week in Houston, there's a Lunar and Planetary Science Conference. It's a huge organization. It has about 1,000 papers. Some are lunar oriented, some are on meteoritics in general, but some of the reservations I have in the back of my mind about the search, rather than just saying, well, I'm worried about that, I just suggest that as a reference point. It's online, and it's a vast library if you haven't already used it. Technicalities that came up with, I guess, while I was listening, was I was kind of intrigued by how you were going to integrate the microscope into the mission. I noticed that on one of the illustrations that its power budget was 3 watts. Of course, if you're using a lab, it would be something of that nature. And then if you integrated it all, I suppose you would file down the weight from its lab bench perspective. But say, for instance, if you're changing slides or if you're changing the magnification, there must be some sort of mechanical interface there that's going to require a drive motor or something of that nature. And there may be some other areas of the payload management that these issues might come up as well. So that might have some bearing on, I guess, on mission performance. Or I'm not even sure whether you have it on the rover or actually on the spacecraft itself.
It is on the lunar laboratory.
It is on the rover?
No, it is on the laboratory, lunar laboratory, which is on the lander. So,
on the lander. Okay, fine. Mm-hmm.
Yeah, so we are not completely sure about how the power budgets of the lander would be. So we were just concentrating on the rover. So that's it.
It looks like an obvious part of the mission, but I'm not sure how much more backup it needs in terms of power and mechanism. That was just something that occurred to me while listening to this. But I guess I'll cut it off from there. I thank you very much for the opportunity to hear about this, and there's a lot to mull in what you've done.
Thank you for your comments, Wes. I appreciate it.
Thank you. Thank you very much.
Sure thing.
Yeah, thank you for being so welcoming. It was a pleasure to present you the project.
Yeah.
Yeah, thank you so much.
Okay, well, thank you everyone for joining us. And in future, actually in next, I don't have yet confirmation, but we do have an expert on a lunar sample collection that is coming here to our platform and talk about NASA plans on the lunar collection, sample collection. So if you guys are interested, and I always extend the invitation to Paul, and hopefully he will share that, and you can hear more about NASA plans. And that will most likely be complementary to what you have proposed in here. With that, thank you so much for joining us today, and I'm looking forward to our next interaction in the following weeks.
Yeah, thank you very much again.
Thank you very much.
Thank you, everyone. Hope to see you all
Thank you.
soon.
Thank you for
Thank you so much.
Thank you.
Bye-bye.
Thank you.
Thank you very much, guys. It was an